So today we're finding the inverse Laplace of quantity s plus 1 divided by quantity s squared plus 4s plus 9. All right, so here's what we like to do, which is we like to go to a big table like this and just match things out. But it is often the case that that does not occur. Yeah, you have your expression that you're trying to find the inverse Laplace is great as your table here is extensive, but you have doesn't match up to what you have. Excuse me. So what's the solution here? So what we often have to do here is we have to use some algebra. Okay. So in our case, because we have a rational expression, a fraction, I'd start by looking maybe at the denominator and see if I could start like factoring the denominator. We got s squared plus 4s plus 9. And that won't factor as a product of two binomials with integers. What I'm saying to that is that it's not going to factor as s plus 3, s plus 1, something like that. Now, it factors over the complex numbers, but we're not going to get into that. So what's the other option we have? Well, one option that's very useful is to complete the square. So I'm going to go ahead and take the denominator, and I'm going to go ahead and complete the square on that. I'm not going to go into that. I'll link a video if in case you're wondering how to do that. And we have that quantity that you see here. Now, this still will not match up to what you have on the table that I showed you a second ago. And the point of this video here is not only does it not match up to the video, but let's say you didn't have an extensive table as is. Yeah, there are some tables that are not as extensive as the one that you saw a minute ago. And so let's just go to that real quick again. And you only maybe have a few of the Laplace transforms here of the options. So for example, 1, 2, 3, 4, and 5. So the Laplace transform of 1, of t to the n, where n is a positive integer, sine and cosine. You know, a lot of the time that's all you have. And maybe option 8, which is the Laplace of e to the at, which is 1 over s minus a. So you only have those few limited options. And yeah, you don't have everything else that's on like 12 through 24 there. So what do? Well, we do is this. And it is very important that you know at least some basic Laplace transforms as the functions that I mentioned, 1 through 5 and number 8. And yeah, you want to know them because a lot of this has to do with just recognizing your transform. Now, if I'm at the point, let me go back here where I have s plus 1 over s plus 2 squared plus 5. I'm going to, the way it works is you kind of look at it and you're going to say, so, you know what? I know the Laplace inverse of s over s squared plus k squared is cosine kt. And the Laplace inverse of k over s squared plus k squared equals sine kt. But that's it. Can I work from there? And you can. Here's how this works. I'm going to transform that expression s plus 1 over s plus 2 squared plus 5 to look a little more like what I have in blue, okay? And there's a couple tricks that we're going to do. The first thing is this. I'm going to transform the s plus 1 on the top. I'm going to rewrite it as like an s plus 2. The reason I'm doing that is because with our transformation formulas, you have s right there. And yeah, I'd like to have the same like expression on the top and bottom. And I did that. So the trick was I added a 2, but sorry, I'm over here now. And I subtracted a 2. And yeah, that balances out. It's adding 0 is the name of the trick. So I have s plus 2 over s plus 2 squared plus 5 minus 1. Yeah, and it's because it's 1 minus 2. Minus 1 over s plus 2 squared plus 5. Okay. Now, I'm going to be doing one more thing here, which is multiplying by 1 on this right here. And the reason I'm doing that trick, multiplying by 1, is because if you look at the Laplace transform over here for sine, let me use the gold color here, the amber looking color. You have, that only works out if you have k over s squared plus k squared. So the number k has to be on top. So in this case, I need to have a root 5, but I can't just put a root 5. I have to balance it out. So I have a 1 root 5 in front of it. Okay. Now that sort of looks like what I have here. Okay. Now, is it exact? No, it's not. So I can't just say it's going to equal sine and cosine. However, I'm to the point where we can use the following. There's a very useful inverse Laplace property, which is this one right here, which is it's called the shift. Okay. So, and this basically says that if you take the inverse Laplace of a shifted transform of a function, it's equal to e to the at times f of t. Capital F just describes the transformation of f of t here, okay, lowercase f of t. So with that information, let's try to see if we can answer a question for the Laplace transform. So I'm going to find the Laplace inverse of s plus 2 over s plus 2 squared plus 5. The way it works is like this. This is how you do it. I'm going to simply ignore the plus 2, the shift, and just look at the s over s squared plus 5. And the Laplace inverse of that is cosine of root 5 t, by that formula that you see right there. Once you do include the shift, that s plus 2 squared plus 5, what happens is this. I'm going to use the formula here that you see in the amber color right there. And yeah, it's basically that s plus 2 over s plus 2 squared plus 5. It's the transformation of the cosine root 5t, but shifted. And basically what this formula says right here, the one again in amber, the shift formula, says, you know what, if you've got the transformation of that's been shifted, all you're going to do is multiply it by the shift constant, which is that minus 2. E to the minus 2 times cosine root 5t, is what I meant to say. So again, if you see the shift that's been done to the transformation, then what you're going to do is you're going to take the function that was transformed, the cosine root 5t, and just multiply by e to the minus 2t. Okay. In very similar manner, L inverse of root 5 s plus 2 squared plus 5. Again, I would just look at the inverse Laplace of the root 5 over s squared plus 5, which would be sine root 5t. But again, that's not what we have. We have an s plus 2. And that shift factor I'm going to include with the e. So it's going to e to the minus 2t sine root 5t. Okay. Now, our final answer is going to be e to the minus 2t cosine root 5t minus 1 root 5 e to the minus 2t sine root 5t. That is our final answer. Now that root 5 there, 1 over root 5, that you see here, is coming from the 1 over root 5 we had here originally in our problem. Okay, that's where it's coming from. All right, so that's how you can handle a inverse Laplace if you're not given like an extensive table. Yeah, often it is the case that you have you reach this point, and you can, and if you have a really extensive table, then 13 and 14 you can just put them in there. But if you don't, this idea of using the shift operator, shift inverse Laplace, if you want to call it that way, sorry, works out pretty well for us. Okay, so yeah, and the other reason I like this shift is because it keeps things down to a minimum, things that you need to know, need to remember and such. And yeah, if you rely on the table too much, often it kind of draws these problems out and it's more time consuming. So anyways, thank you so much for your time. Appreciate it.